A plate shaped like an equilateral triangle 1 meter on a side is placed on a vertical wall 1 meter below the surface of a pool filled with water. On which plate in the figure is the force greater? Try to anticipate the answer, then commute the force on each plate.
We think that there will be more force on this triangle opposed to this triangle because water is going to be on top of the triangle, more water from here to here throughout the whole 1 meter compared to just 1 meter of water on top of this triangle.
Alright, so we took our triangles that were under the water and moved them onto our x and y coordinates. And we did this to figure out the length of this middle piece right here, which is b. So we used Pythagorean's theorem, which is a squared plus b squared equals c squared, and it gave us our length of square root of 3 over 2 for both triangles.
Alright, so we know force is density times gravity, the integral of density times gravity times length times width. And then our length is going to be our height of our triangle, so square root of 3 over 2 plus the 1 meter underwater that we are, plus 1, and minus y, because it counts for from y going down. And then our width will be, how do we explain that? Our width is going to be y minus 0 equals negative 3 for our slope, negative square root of 3 because of our slope, and then x minus 1/2, that's right there, 0, 1/2, done. And then this comes out to be x equals 1/2 minus x equals 1/2 minus y over square root 3.
And that is for our first triangle.
For triangle 1.
For our second triangle,
Our length will be the same because we're going up root 3 over 2 plus the 1 meter, and minus y. And then our width this time will be our equation of y minus 0 is equal to root 3 positive this time since our slope is going up, and then x minus 0 equals x equals y over square root of 3.
alright, so we took our length and our width and decided to plug it into our equation right here. So we have the length, which is root 3 over 2 plus 1 minus y times 2. We got this 2 because this is an equilateral triangle and it is symmetrical about the y-axis, multiplied by the width. That's why we took the 2, because we found the width from right here. We need to multiply it by 2. So we plugged it in, we expanded it, and we also moved the 2 out to the front because it's a constant. And this is what we got. Took the integral of this into this equation right here and solved it. And we got p times g equals the square root of 3 over 2 minus 3 over 4 root 3 plus 3 over 4 times, the density and the gravity.
So this is our integral for the second triangle, the upside down triangle. We have our constant, we plugged in our length and our width. This 2 is here because it is symmetrical about the y-axis. Then we just brought the 2 out, expanded, solved our integral, and then plugged in the numbers, and then solved it. And this is what we end up with, which is density times gravity times 1/8 plus 3/4 root 3. And
Alright, so when we put our numbers back to our triangles, you can see that our assumption was right. In our first triangle, there was more force pushing down. And with the second triangle, as you can tell, the shark is going after it.